got all these stages that you are seeing right now. So we have analysis, design, coding, testing, maintenance. These are the stages of waterfall model, and you have to know them. As in, you have to know the first, then the second, then the third, and so on up to the end. But each stage looks up to the previous one. So as you are designing, you are still in a cycle back to analysis and to design. When you are done designing, you go to coding, you are looking at your design and going backwards like that, and then testing and so on until you reach maintenance. The arrows show that each stage has put input in both the following stage and also the previous stage. Okay, so that is the waterfall model. So the benefits. It's important to understand as the stages are clearly defined. It's easy to manage as well. Okay, because the stages are actually fixed. The stages are processed and completed one at a time, and it works well for smaller projects because you are done with the first stage analysis, you go to design, then you go to coding, then you go to testing, and then you go to maintenance. It is really just like that. But the drawbacks, no working software is produced until late during the life cycle, because imagine you're going to design, you're going to code, testing, maintenance will really come towards the end of it. I mean, testing of it, so that you have working program at testing here, it's coming really towards the end of the whole thing. So, and it's not good for complex programs which are like object oriented, because you want to start some of the programs, you want to start coding almost early on from analysis. As long as the analysis stage is done, when you go into design, test plan, and some kind of a coding plan are usually already done in certain models, but this one restricts the actual coding towards the end of it. Okay, so it's a poor model for long and ongoing projects, because it is not a cycle like the one we looked at the beginning. Okay, it cannot accommodate changing environments. It is difficult to measure progress within stages, um, because you are looking at each stage almost on its own, except for the previous one and the next one. So you're not looking at it as a ring, you're looking at each of them as just a stage. So integration is done at the very end, which doesn't allow identifying potential technical or business issues early. So yeah, the integration is really late. So if you look at how it looks here, analysis, then design. Each one is standing on its own. Okay, so it's not a ring. And then you come to coding, then you come to testing. The backward is too short, and then each stage seems to really be standing alone there. So this is the waterfall model, and these are some of the drawbacks that it has. You can research and see any other things that you can add, but please make sure you have about 4 benefits, 4 drawbacks for the waterfall model. Okay, then the iterative model. Okay, we know what iteration means. It's more like a loop model. It does not attempt to start with a full specification of a requirement. So it starts without the full specification. So instead, development starts with the implementation of a small subset of the program requirement. So a small subset is begun or is started even before you have the full requirements list. So you say, okay, we need a door. Start making a door as we are looking at the other parts of it. So you can start the interface as you are still looking at the processes inside. As long as analysis has gone through, you do not wait for full specifications. So it's repetitive. Reviews are also repetitive. So everything is being reviewed. As you make every procedure, it is being reviewed, even as you are still getting more requirements. Okay. So finally, you have a complete system. All right. The benefits, there's quite a lot of benefits, but you're going to see that mostly it's about it being able to to work on critical projects. It's because it's easy to measure it. It is results oriented and such. So there are a lot of benefits here. There is a working model of the system at every stage of development. This is a good benefit. Some working functionality can be developed quickly and early, yes, because you are working on every requirement that comes out. Results are obtained early and periodically, yes. Parallel development can be planned. You can be working on this procedure and this procedure at the same time. Progress can be measured. Less costly to change the scope. It's less costly because if you have only done a procedure and you want to make changes to it, the changes will not require a lot of backtracking. But if you were doing the waterfall model, where you have done a lot of analysis and design already before you came to coding, you did a lot of it when you come to testing. So the waterfall model, you're going back to make a correction may be a long way because there are a lot of things you've done already. Okay, testing and debugging of a smaller subset of program is easy. Yeah, those tests that we talked about will be easy. Okay, because then you are looking at them as a procedure, as a function. Risks are identified and resolved during iteration. Easier to manage risk, high risk parts are easy to do. With every increment, operational product is delivered. So every procedure that is needed there, every functionality is achieved and delivered. So issues, challenges, and risks identified from each increment can be utilized or applied to the next increment. It's better suited for large and mission critical projects. During the life cycle, software is produced early, which facilitates customer evaluation and feedback. So you already have some feedback even before you are done with everything because of functionality which has been attained from the earlier stages of it. Okay, it has some drawbacks as well. Um, Only large software development projects can benefit because it is hard to break a small software system into further small serviceable modules. So it's good for a large project, but for a small project, it's not too good because breaking it down will really be another daunting task. So it's better you keep like waterfall model for smaller projects. More resources may be required, yes, because you need to be doing certain things concurrently. So you need more resources at the same time. Design issues might arise because not all requirements are gathered at the beginning of the entire cycle. Okay, and they may arise for sure because the requirements for this one are done, and then you have to go for the next set of requirements and so on. So design may be a thing that is coming once in a while during the entire process. So, defining increments may require definition of the complete system. So, this is a serious drawback because if you want to do an increment, because as you are going down, you are doing the iterations going backwards and forth. So, you may find that certain increments will actually need the changing of the entire system. This may be a big problem there. But then experts will already know how much of the system to have for them to start. Okay, so this is about it. Then we have now the RAD model, Rapid Application Development Model. It uses minimal planning. What it does is it's a prototype type of development. So a prototype is a working model of part of the solution. It's not really part as in a piece of it. That would be iteration based RAD. But this one is this one is one where the prototype is more like almost whole encompassing. Okay, so it says in the RAD model, the modules are developed in parallel as prototypes integrated to make the complete system for faster product delivery. All right, what you're just trying to do is say parallel prototypes, as in you are looking at the whole system and trying to make use of something. It's like you are going to build this house and you make a small house which may not have all the details, but you make on a table a prototype which people can look and say, yeah, this is the house we want. So it's a smaller part of the whole part, but it's showing you where you are going. So there is no detailed pre-planning. Changes are made during the development process. The analysis, design, code, and test phases are incorporated into a series of short iterative development cycles. Yeah, so it encompasses iterations as well, because when you have a prototype which shows where you are heading to, then you keep on improving on it. So it's rapid application development. Right? So the word rapid will help you remember that it uses minimal planning. Okay, because you are rapidly getting into building it even before you are done with everything, because you want to see the whole part before you actually, as you are starting to develop, you want to see it in full, and then you start on making the actual details. Okay, so it's prototype based. All right, benefits. Changing requirements can be accommodated. Yes, easily already you can see. Progress can be measured. It is easy to do that. Productivity increases with fewer people in a short time, reduces development time, increases the usability of components, quick initial reviews occur, encourages customer feedback, integration from a very beginning solves a lot of integration issues. So what we can see from these benefits is actually interaction more with customers, issues of development time, measurement of progress, because you're making a prototype, it's already seen, so you can already start receiving feedback from the prototype. If you have internal testers, for example, internal users who are trying the system, they already have a look at it even before it is done. It is not even there, the details are not yet known, but they will already have a glimpse of how the whole thing will look like because there's a prototype. So it will be then a short distance from that time to the time the whole thing is done, because they've already seen a prototype, so they're already discussing and making requirement changes, and feedback is easy to get. Drawbacks: only systems that can be modularized can be built using RAD. Okay, so by modularizing we mean modules and procedures, processes which can be done in pieces, because you would say it's more like in the iterations, where when you see this procedure, then you encompass it to the prototype. Okay, so if you cannot see them in modules, you will not be able to see the prototype. Okay, and requires highly skilled developers, yes, because they want to put the whole thing together before it is actually fully planned. Okay, with minimal plans. Suitable for systems that are component based, just like we talked about modularization, component based and scalable as well. Okay, requires user involvement throughout the life cycle. Thank you, because from the beginning you are looking at the feedback. Suitable for projects requiring shorter development times. All right, so we've looked at the three of them, and we are now looking at the types of programming errors. So we have a few errors. The first error type that we have is the syntax. Syntax, as in normal language, means the actual language. Okay. So, for example, here there's an example of the word print. If it is then typed as print, this is a syntax error, and the translator will be able to recognize this. If it was a keyword, print is a keyword like dim in VB, and then instead of dim you put din, then the translator will not know that this is a declaration of a variable, for example. So this is a syntax error. So syntax error would be like, if you look at um, uh, the way this is written. So if a programming language uses x is equal to 3 multiplied by brackets 2 plus a, then instead you start with 3 multiplied by brackets 2 plus a is equal to x. If a programming language is programmed or meant to look at it this way and not that way, then this will still be a syntax error, because things have been reversed and not written in the correct order, even if mathematically this is still looking okay. That is a syntax error. Then we have logic errors, which are the ones which we usually look at when you have questions of correcting an algorithm. We usually look for logic errors, because logic errors are the flow of the program. So they are, how is the program flowing? If, for example, making a decision, it causes you to make a wrong decision because the program is not well, then that is a logic error, because the logic is not being met. What you are looking for is not being done. Okay, so you are not attaining the result of running that program. That is a logic error. So another thing is like here, look at this statement: total number is equal to previous total minus new number. No, if total number is expected to be the previous total plus the new number, so that now you have a new total, because totals are increments. This is totaling, isn't it? More like totaling, because it's previous total and new number. So here it's supposed to be a plus, an addition, but instead you are actually subtracting. This is a logic error because it will work. It's not syntactically wrong. It is correct. All the words are okay. These would be declared variables which you are using, But then this is logic because you're not supposed to subtract, instead you should add. This is an example of a logic error. Then we have the runtime errors. These are the errors which usually should identify to say if the computer runs into this as the program is running, because the program is okay, but if it allows this kind of entry or allows a certain type of calculation to happen, it may go into maybe say a loop which is not completing. All right, like here, say dividing by zero, so that it is impossible, and therefore the program will just crash. So runtime errors may cause the program to crash or to stop responding because um, well, the logic is okay, the syntax is fine, but you did not catch certain errors. You did not see anticipate that somebody may enter a zero in a division situation, for example. Okay, so those are the errors, but how do we prevent the errors? So to prevent the errors, errors can come in any of these situations, okay? But to minimize that, we have to use methods that are acceptable, like structured programming or object-oriented programming. So in structured programming, you have the functions that you program function by function, tail on end, and you also have OOD, object-oriented programming, where you program and make objects and call them as you are using them. So you use what is established. All right. Use the other one here says conventions such as identifier table. So what you are encouraged to use are the things that you are learning, identifier tables, okay, so that you can know what is this identifier's name, what is it supposed to be doing, have a description of it, you have the type, is it an int, is it, so you use all those things so that you can already see and anticipate certain errors. Tried and tested modules or objects from libraries, so you can take advantage of the libraries that already exist in the programming language, so you use that. So because they are already tested for some time, they've been on in use, it is easier. All right. So then there is now the types of maintenance. So we're going to talk about corrective maintenance, adaptive maintenance, and so on. So corrective maintenance is when the program is not working correctly due to a logic error or a runtime error. Remember, runtime error, really, you could say it looks like a subset of a logic error because there's then something that has been missed out. So corrective maintenance is when um, errors will kind of surface as you run the program. You're getting some wrong result, so you have to correct it. That is corrective maintenance, because there's unexpected result that the program is bringing, or maybe the program has crashed. Let's correct it. There's adaptive maintenance, which you see that we need to improve from um, Windows 2000 to another version, from 95 to 98 or so, and so on and so forth. Now there it's adaptive because you're looking at the changes, maybe changes in certain aspects of the market even. So you have to do adaptive maintenance to enhance functionality or to respond to specific changes, whatever those changes are. Then also just to perfect the program. So the program runs satisfactorily, yes. However, there's still room for improvement. So this is perfective maintenance. Okay, let's do this better. And this is a very common maintenance thing. All right. So now let's look at program design using structure charts. So there are structure charts such as this one. It's a graphical representation of the modular structure of a solution. So there is a solution which we need here. Okay. So let's look at, there are some parameters that are being passed here. For example, this program, what we need to do is calculate the average. So it's called averages program. But in these average programs, what really are its legs? What is it doing? It's supposed to accept inputs, calculate average and output. So you've put it in more like you've modularized it. You're going to say there's an interface. This interface should show that input two numbers, get an average. So these directions here, arrows with those circles, they are showing us now where the input are supposed to, the direction they're supposed to be going. So this input, they're going into the program. Okay. Then that program now runs, calculates an average. So it uses the two inputs to calculate the average. Then its output is the actual average. Now this average is then output here. Okay, so this is a level one, which is more like what is contained in the program. Well, there's input, then there's calculation and output. It's the main architecture, so to say, it's the main layout of the program. So we have a few definitions of an arrow with a solid round end, like this solid. Okay, it shows kind of a Boolean value, and then we have these with two double arrows on either side. Okay, and it shows that the variable value is updated within the module. So within that module, the value of that variable is updated. So we can look at this, a lot of exam questions to get over this. So we have some of the diagrams looking really big like that, because here we are looking at connect 4 and it has all this under it. All right, so we have those repetitive actions here. While game not finished, you continue on. So these, all these will continue repeating. Okay, so you have utilize board. So the board comes in, and then there is also a setup of the game is also set up. Then now the player is making changes, and this happens within the game. This player, this is an instance of a player now doing the actual work, and then there's an output here on the board. There's another output here, then the game is finished. So you can study this on the slides and just try to make sense of that. Okay. Um, Now, program design involves state transition diagrams. Okay, now when we talk about state transition diagrams, there's first the finite state machine. Okay, the finite state machine consists of a fixed set of possible states with a set of inputs that change the state and a set of possible outputs. So it's a finite state machine. Um, so we're talking about a diagram that should have a certain set of possible states, and these states are going to change with certain input to give possible outputs. So we have a state transition table side by side. So the state transition table gives information about the states to say, okay, the finite state machine can only receive such inputs, and then this is what is expected to come out. So it will give you that information. Then we have the state transition diagram now itself. So the state transition diagram describes the behavior of an FSM, which is a finite state machine. So the finite state machine has a diagram, and it also has a table that explains what it is. Okay, here it is now. So you have a state transition diagram, and then you have a table here. Isn't it? This is what we said. So we can see that um, there is S1, and then there's S2. So these are states, isn't it? So this state there is this A, which its output is still within the same state, and then we have B, which goes on to S2, and then within S2 there's another one which is working just there, and then there's that backtrack to A. So you can look at that. The input is A and B. So the input is A and B. They're the ones in small letters there, and so state one. Uh, with that input. So input and state one is just around state one. So there is also S2 with that input changing state to S1. So S2 with the input A changing to state one. Okay, but for B, input S1 gives S2. So for B, um, so input S1, yeah, gives S2, and also input S2 gives back the state S2. All right, so this is then this is a halting state. This is where we're starting from, and this is a halting state, like the final state. This one, which has two rings for the two circles encompassed. All right, so you can have a look at it this again just to see. It's still the same one, but what this shows is when you have a vertical line, we say a vertical bar. When you have a vertical line between two inputs, okay, it means the first one is the input, the second one is the output. So you expect output C from input B, okay, as it transforms S1 to state 2. So state 1 is being transformed to state 2. If the input is B on state 1, then the output will be C in step 2. All right. So even here within state 2, B is putting, and the output is still state 2, but it is F. Okay, so B was the input in state 2. It will still be in state 2 for the output, but it will be output F. Okay, so some of the state transition diagrams then that you can create to say the current state, the event, and the next state. So the current state is system inactive. Press that button, the system is active. That is, there's an event that you did, so that you know the next state. So if the system was active, then you enter pin, then the system becomes inactive. I've closed it. The system active, active sensor, then alert mode. So all those are just part of the state transition diagram. There you are again. This is what you can show on this state FSM machine. Okay, final state machine. So the STD, state transition diagram, here is quite massive. You can just look at it, and each state will need a certain event to come to another state, another event to come to another state. Some of the events will just be repetitive around a certain state. They'll give back the same state. Thank you so much, and bye bye.